Hello friends, in this video lecture we are going to study about why at optical frequencies the emission is predominantly due to spontaneous transitions and hence the light from the usual light source is incoherent, and we will derive the relationship between the Einstein coefficient A and the spontaneous lifetime for the level 2 laser. Also, we will study about the line shape function and its functionality. We will derive the equation for the rate of change of intensity of the radiation as it passes through the medium. Further, we will study about the threshold conditions for the population inversion, and we will derive an expression for the passive cavity lifetime, and we will also study about the line broadening mechanism such as homogeneous broadening and inhomogeneous broadening. Under this, we will discuss detail in terms of natural broadening, collision broadening, Doppler broadening, and we will also study about the rate equation for the level 2 and level 3 laser system. So let's start the video lecture. Myself Virendra Kumar, professor and scientist, and we are studying about the laser system. As we already know that the ratio of number of spontaneous emission to number of stimulated emission is given by R is equal to A N2 divided by B N2 U omega is equal to e to the power h cross omega by k bt minus 1, where A and B are the Einstein's coefficients, E is the energy density per frequency, and Kb is the Boltzmann constant. Here we will know that for the visual wavelength, the emission dominated is because of the spontaneous emission, and hence there is no coherency in the light emission. So let us consider a current is passing through a filament and its temperature is suppose 1000 Kelvin. So at this temperature kVt by h cross is equal to 1.38 into 10 to the power minus 23 joule per Kelvin into 1000 Kelvin divided by 1.054 into 10 to the power minus 3 4 joule second, and that gives 1.3 into 10 to the power 14 hertz. And also for visual light, suppose given wavelength is 500 nanometer or 5000 angstrom. Therefore, the angular frequency omega for this wavelength lambda is equal to 5000 angstrom can be calculated as 2 pi c by lambda, that gives equal to 4 into 10 to the power 15 per second. Hence, we see that omega is greater than kVt by h cross value, and in this case, as we know, for the ratio of the spontaneous emission to stimulated emission, that is e to the power h cross omega by kt minus 1, and that's in this case will be equal to e to the power h cross omega by kt, and hence in this case spontaneous emission is dominating, and the value for this ratio after calculation e to the power 3.8 into 10 to the power 15 divided by 1.3 into 10 to the power 14 comes out nearly equal to e to the power 29.2, and that is equivalent to 5 into 10 to the power 12 Therefore, spontaneous emission is this much times of the stimulated emission. Thus, at optical frequencies, the emission is predominantly due to the spontaneous transitions, and hence the light from usual light source is incoherent. Now we will derive the relationship between the Einstein coefficient A and the spontaneous lifetime of level 2 laser system. So let us derive. To derive this relationship, let us consider two states of an atom with energies E1 and E2 with corresponding population densities of N1 and N2 respectively. An atom in state 2 can make spontaneous transition to only level 1. Then the number of atoms making transition for spontaneous emission per unit time per unit volume is A21N2. Therefore, the rate of change of population of level 2 with the time due to spontaneous emission is given by dN2 by dt is equal to minus A21N2. This is equation number 1. To solve this equation, let us write this as dN2 by N2 is equal to minus A21 dt and integrate this from N2 at time t is equal to 0 to N2 at time t, and this from time t is equal to 0 to time t. So after integration, this gives log N2 at time t minus log N2 at 0 is equal to minus A21 into t. After simplification, we can write this as log N2 at t divided by N2 at 0 is equal to minus A21 t, which implies that N2 t is equal to N2 0 e to the power minus A21 t. This equation gives the variation of population in level 2 with the time t. Thus, the population of level 2 reduces by 1 by e in time t is equal to 1 by a to 1, which is called spontaneous lifetime associated with transition from the level 2 to 1. Now, if one observes the spectrum of the radiation due to the spontaneous emission from a collection of atoms, one finds that the radiation is not strictly monochromatic but is spread over a certain frequency range. Similarly, if one measures the absorption by a collection of atoms as a function of frequency, it is found that the atoms are capable of absorbing not just a single frequency but radiation over a band of frequencies. This implies that energy levels have width and the atoms can interact with radiation over a range of frequencies, but the strength of interaction is a function of frequencies. This function that describes the frequency dependency is called the line shape function and is represented by g omega. The function is usually normalized according to integration g omega d omega is equal to 1. Therefore, out of the total N2 and N1 atoms per unit volume, only N2 g omega d omega and N1 g omega d omega atoms per unit volume will be capable of interacting with radiation and having frequency between omega and omega plus d omega. Hence, the total number of stimulated emission per unit time per unit volume in terms of the line shape function is given by gamma 2 1 is equal to integration b to 1 u omega n to g omega d omega, where substituting the values of b to 1 we get n to pi square c cube by h cross omega cube n0 cube a to 1 u omega g omega d omega, which gives integration into pi square c cube divided by h cross omega cube n0 cube 1 by spontaneous lifetime tsp e omega g omega t omega. So after substituting the values a21 is equal to 1 by tsp. Now we will discuss two important specific cases. Case number 1. If the atoms are interacting with radiation whose spectrum is very broad compared to the spectrum of g omega, then one may consider that over the region of integration where g omega is appreciable, u omega divided by omega cube is taken as a constant, and thus the equation gamma 2 1 is equal to integration n2 pi square c cube divided by h cross tsp n0 cube u omega g omega d omega divided by omega cube. That means we will take out n2 by n0 cube pi square c cube by h cross tsp u omega by omega cube for this specific case when the spectrum of the interacting radiation is broad in compared to the g omega, and then integrating part g omega d omega, that will give gamma 21 is equal to n2 pi square c cube by n0 cube h cross omega cube tsp u omega, where omega is the transition frequency. This equation represents the rate of stimulated emission per unit volume when the atom interacts with the broadband radiation. Now we will take up the second case, the case number 2, that is when the atom is interacting with near monochromatic radiation. Then in that case g omega is broader and E omega is within this G omega. In that case, we will take G omega by omega cube as a constant. Let omega prime is the frequency of radiation. Then E omega curve will be sharply picked at omega is equal to omega prime as compared to G omega. In that case, the rate of stimulated emission per unit volume will be given by gamma 21 is equal to n2 pi square c cube by h cross omega prime cube tsp g omega prime integration u omega d omega, which gives gamma 21 is equal to n2 by n0 cube pi square c cube divided by h cross omega prime cube tsp g omega prime u omega. This is the rate of stimulated emission per unit volume when the atom is interacting with the near monochromatic radiation. Here it is important to note that U omega is equal to U omega d omega is the energy density of the incident radiation near monochromatic, and the dimension of U is equal to energy per unit volume, while dimension of U omega is the energy per unit volume per unit frequency interval. Now we will study about the light amplification, and we will derive the expression for the rate of change of intensity of the radiation as it passes through the medium. So let us draw this diagram where this is the mirror and this is also mirror. This has the high reflectivity and this has the partially less reflectivity, and this is the active medium. So let us consider two planes P1 and P2 of the area S. situated at Z and Z plus dz, Z and Z plus dz. Area is S. Now, and let Z is the direction of propagation of the radiation. Let Iz and Iz plus dz represent the intensity of the radiation at Z and Z plus dz respectively. Net amount of energy entering the volume S into dz between P1 and P2 will be given by Iz minus Iz plus dz into S. So this is the amount of energy entering the volume S into dz, where S is the area. Since Iz plus dz can be given by Iz plus del I by del Z into dz, therefore this equation reduces to Iz minus Iz plus dz into S is equal to Iz minus Iz minus del I by del Z into dz into S, which gives equal to minus del I by del Z dz into S, where dz into S is the volume. This must be equal to the net amount of energy absorbed by the atoms in the volume dz into S. Therefore, the energy absorbed per unit time in the volume element SdZ is given by gamma 1 to h cross omega SdZ. Similarly, energy released through stimulated emission is given by gamma 21 S dz into h cross omega. Therefore, the net energy absorbed per unit time in the volume S dz will be given by gamma 12 minus gamma 21 h cross omega dz into S, which is equal to pi square c cube by h cross omega cube n0 cube into 1 by T spontaneous emission u at omega g omega h cross omega s dz into n1 minus n2, which will be equal to pi square c cube divided by omega square n0 cube tsp u omega g omega into n1 minus n2 sdz. So this is the net energy absorbed per unit time in the volume element sdz. Hence, equating this equation with the previous this equation, we get del I by del Z sdz is equal to minus pi square c cube by omega square n0 cube tsp into e omega g omega into n1 minus n2 sdz. Therefore, del I by del Z is equal to minus pi square c cube by omega square n0 cube tsp u omega g omega into n1 minus n2. Now the energy density U and the intensity of radiation I are related through the following equation, that is the energy flux is equal to energy density into velocity, that is equal to V into energy density, that is equal to C by N0 into U at omega. Therefore, del I by del Z equation becomes equal to minus pi square C square by omega square N0 square TSP I g omega n1 minus n2. So we just substituted the value for c by n0 into u omega is equal to I. So in this, so this equation becomes del I by del Z is equal to minus pi square by c square omega square n0 square tsp into I into g omega n1 minus n2. And since this all is constant, therefore this del I by del Z can be written as equal to minus alpha into I, where alpha is equal to pi square c square by omega square n0 square tsp into g omega n1 minus n2, known as the amplification factor of the medium, where omega is the frequency of the incident radiation. Now we'll consider n1 minus n2 is greater than 0. That is the number of atom in the state 1 is greater than number of atom in the state 2, then alpha will be positive and hence intensity decreases with the jet. On the other hand, if n1 minus n2 is negative, that is number of atoms in state 1 is lesser than the number of atoms in the state 2, in that case alpha amplification factor will be negative and del I by del Z will be positive. That means the beam is amplified with the Z distance. We will draw here in this diagram. You can see that variation of alpha with omega. So for n1 greater than n2, this gives alpha as a positive, and in that case variation of intensity with Z is negative. That means the intensity is going to decrease with propagation of the radiation if the n1 is greater than n2, and for n1 is less than n2, the alpha is negative in this diagram. That gives variation of intensity with Z is positive, that means in that case amplification of the radiation is going on. Thus we see that del I by del Z is equal to minus alpha I, where alpha is the amplification factor. Alpha is equal to pi square c square by omega square n square tsp into g omega n1 minus n2. For the n1 is greater than n2, del I by del Z is negative as alpha is positive. So in this case, the beam is getting attenuated with the propagation along the z direction. But in the case of n1 is a greater than n2, del I by del z is positive, and because alpha is negative, beam of the light is getting amplified, and this condition is known as the population inversion. So this is the condition of population inversion, and in this case, beam is amplified. Now we will derive the equation for the intensity at any distance z in terms of initial intensity. So this equation can be written as di by I is equal to minus alpha dz integration the intensity at z is equal to 0 to z is equal to z, and therefore this equation becomes this, and we after integration we can write this as log iz minus log I at z is equal to 0 is equal to minus alpha z, which gives that log of iz by I0 is equal to minus alpha z. That means I is equal to iz, I at z is equal to I0 into e to the power minus alpha z. So this is the equation of variation of intensity with z, that is an exponential attenuation when n1 is greater than n2, and an exponential amplification when n2 is greater than n1. That is the case of population inversion when n1 n1 is less than n2. So you can see that light is amplified exponentially when the number of atoms in the state 2 is higher than the number of atoms in the state 1. So that is the desirable condition for the laser, and that condition is the population inversion. Friends, now we will study about the threshold condition for the population inversion in the laser, and we will derive the equation for passive cavity lifetime. Friends, you have not subscribed the channel till now, please subscribe it and press the like button and share this video with your friends and colleagues so that they can also learn about the lesser important topics. So we have known that for a medium to be capable of amplifying incident radiation, we should create a state of population inversion in the medium. Such a medium will behave as an amplifier for those frequencies which fall within its line width. So in order to generate radiation, this amplifying medium is placed in an optical resonator. I have discussed about the optical resonator in the previous video lecture, which I will provide the link in this video description, and you can also watch those videos by clicking the I button in the right corner of the screen. Now, so optical resonator, which consists of a pair of mirrors facing each other, much like in a Fabry period echelon. So radiation which bounces back and forth between the mirrors is amplified by the amplifying medium, and also it suffers some losses due to the finite reflectivity of the mirrors and other scattering and diffraction losses. If the oscillations have to be sustained in the cavity, then the losses must be exactly compensated by the gain factor. Thus, a minimum population inversion density is required to overcome the losses, and this is called the threshold population inversion. So let us consider in cavity we have two mirrors M1 and M2 and kept apart at a distance d. Let R1 and R2 are reflectivity of the mirrors and let alpha c represents loss per unit length. As scattering loss, diffraction loss due to finite mirror sizes. Let I be the initial intensity leaving mirror M1. Therefore, intensity after traveling a distance d can be given by I R1. So this is the initial intensity. Traveling distance d, the intensity, suppose this is ID, I R1 e to the power minus I alpha d into e to the power minus I alpha c into d. So this is presenting the loss. This is presenting the loss factor. This becomes the initial intensity for mirror M2. So in backward journey, intensity will be given by I R1 e to the power minus alpha omega d. So this is alpha omega d into minus e to the power minus alpha c d into R2 e to the power minus alpha omega d into e to the power minus alpha c d. So after one complete round trip, we have after one complete round trip. So first this represents if it is the radiation is going this way and suffering the some losses in terms of e to the power minus alpha c into d. After reflecting from this M2 mirror, it is coming back to the first mirror, and in that way it is also again suffering some loss e to the power minus alpha c d, and this will be represented here as the initial intensity. So after complete round trip, the intensity is given by R1 R2 e to the power minus 2 alpha plus alpha c into d. This is suppose this is equation number A. Hence, for lesser oscillation to begin, the intensity should be greater than this one complete round intensity. Therefore, for lesser oscillation to begin, total intensity I R1 into R2 e to the power minus 2 times alpha plus alpha c into d should be greater than, therefore minus alpha omega should be greater than to alpha c minus 1 by 2d log of R1 R2. So this is the condition for the lesser amplification or lesser acceleration. Thus we see that the RHS of this equation depends on the passive cavity parameters only, where alpha c is the attenuation factor of the medium. This can be related to passive cavity lifetime Tc. So if Tc is the passive cavity lifetime, then it is defined as the time required to reduce the energy in cavity by a factor 1 by E. So Tc Passive cavity lifetime is the time required to reduce the energy in cavity by a factor 1 by E. In the absence of amplification by the medium, the intensity at a point reduces by a factor R1, R2, e to the power minus 2 alpha c into d. That is given by e to the power minus 2 alpha c d minus log R1 R2 in a time corresponding to one round trip time. So this is the amount by which the intensity or energy reduces in a complete round trip in absence of any amplification by the medium. So one round trip time corresponds to t is equal to total distance covered divided by the velocity, that is equal to 2d is divided by c by refractive index, that gives time is equal to 2d n0 by c, where n0 is the refractive index of the medium. So if the intensity reduces as e to the power minus t by tc, then in a time t is equal to 2d n0 by c, the factor by which the intensity will be reduced, factor by which the intensity will be reduced is given by e to the power minus 2d n0 by c into tc. Thus, it is it can be written as 2 e to the power minus 2 alpha c d minus log r1 r2 will be equal to this factor e to the power minus 2d n0 by c into tc. So equating this equation, we have 1 by tc is equal to c by 2d n0 2 alpha c d minus log r1 r2. This is the passive cavity lifetime, which is further can be written as is equal to 2 d n0 by c into 1 by 2 alpha c d minus log of r1 r2. So this is the expression for the passive cavity lifetime. Now at threshold, the loss is equal to gain, that is the population inversion condition n2 minus n1 should be greater than equal to 0 will yield, in case of threshold, n2 is equal to n1, and that is in equilibrium concentration it will be written as equal to n by 2. Therefore n1 is equal to n by 2 and n2 is equal to n by 2. So there has to be a minimum population inversion to maintain the losses. So gain is equal to minus 2d alpha c, and loss is equal to 2d alpha c minus log r1 r2. At the threshold, these gains and losses should be equal, that is minus 2d alpha c is equal to 2d alpha c minus log r1 and r2. Now substituting the values for alpha from here, we get minus 2d alpha omega is equal to minus pi square c square divided by omega square n square 2d by tsp g omega n1 minus n2 and RHS. This is LHS. This is RHS. 2d alpha c minus log r1 and r2 will be equal to 2d n0 by ctc. LHS equal to RHS gives minus pi square c square by omega naught n square 2d by tsp into g omega n1 minus n2 is equal to 2d n0 by ctc, which implies that n1 minus n2 is equal to minus 1 by c cube tc into n0 cube by pi square omega square tsp by g omega, which finally gives n1 minus n2 is equal to minus omega square tsp n0 cube by pi square c cube tc into 1 by g omega. Therefore, after converting this into frequency omega is equal to 2 pi nu, we get n2 minus n1, taking negative sign into inside this n2 minus n1, that gives 4 pi nu square n nu naught n naught cube c cube tsp by tc into 1 by g omega. Equation for the threshold condition. Thus, in order to have a low threshold value of population inversion, the following condition should hold good, and that are Tc should be large so that n2 minus n1 will be less. So this Tc is the passive cavity lifetime, and for a lesser value of threshold, this should be higher. That means cavity losses must be small, and g omega should be also large. That means as g omega is nearly equal to 1 by delta omega, so a smaller width gives a smaller value of n2 minus n1. So a smaller width of the frequency range will give the small value of the threshold. So a smaller width is required for the lower threshold value. So a smaller value of TSP will also give the smaller value of threshold, that is spontaneous lifetime smaller. that is strongly allowed transition. At the same time, for a small TSP, larger pumping power will be required to maintain a given population inversion. Fourth and last important condition to meet for the lesser threshold value is that it is much easier to obtain laser action at infrared wavelengths than in the ultraviolet region. That means if the nu is lesser, we can get easily threshold condition. So friends, these are the things which I wanted to share with you in this video lecture. Hope you enjoyed this video and learnt about the derivation and all these important topic of lesson. If you have any doubt, queries, please let me know by providing your feedback and comments in the comment box. You can also follow Sai Academy social media channel like Facebook and Instagram, and you can also put your queries there. Friends, if you have not subscribed this High Academy channel, please subscribe right now so that you can get the notification of the upcoming videos on the time, and also share this video with your friends and colleagues. And please don't forget to press the like button for this video. Thank you.